This video is for section 2-5, combining open sentences. In previous lessons, we've graphed sets of numbers on the number line. Let's extend this to the solution set of an open sentence with absolute value in it. To graph the absolute value of x minus 1 equals 3, we could think of the absolute value portion as the distance between x and 1 on a number line. Remember that subtraction means the difference. The difference between x and 1 means the same thing as the distance between x and 1. If this distance is 3, then the point x must be located 3 units to the left of 1 or 3 units to the right of 1. This diagram shows this idea. Here is 1 on the number line. We're looking for point x 3 units from that number. If you move to the right 3 units, the answer for x is positive 4. If you move to the left 3 units, the answer for x is negative 2. Both of those numbers are 3 units from 1. Therefore, the absolute value of x minus 1 equals 3 is equivalent to this combination of sentences. X minus 1 equals negative 3 or x minus 1 equals positive 3. This first open sentence fits the idea of moving left 3 units from 1. The second open sentence fits the idea of moving right 3 units from 1. Let's solve this combination by adding 1 to both sides. This makes x equals negative 2. And then for this piece here, let's also add 1 to both sides. This makes x equals 4. Notice the word or used to connect these two results together. X equals negative 2 or x equals 4. This algebraic solution fits our graphical solution in our diagram. The solutions of an inequality, the absolute value of x minus 1 is less than or equal to 3, correspond to all points at most 3 units from 1 on a number line. We can show this in the diagram. Here is where 1 is. We want to locate point x so that the distance from 1 to point x is at most 3 units. So if we go 3 units to the right, then this dot here at 4 is the maximum value for point x. Once we travel past the 4, we are now greater than 3 units from 1. Starting at 1, we can go 3 units to the left. And here's a dot at negative 2. Once we go past negative 2, we are now greater than 3 units away from 1. X can be any number in between those boundary dots. Therefore, the absolute value of x minus 1 is less than or equal to 3 is equivalent to this combination of open sentences. X minus 1 is in between negative 3 and 3. We can solve this for x. Let's add 1 to all members of this combination. Negative 3 add 1 is negative 2. In the middle, x minus 1 add 1 makes x. On the right, 3 add 1 makes 4. Notice that this answer corresponds to our diagram. The solutions of the inequality, the absolute value of x minus 1 is greater than 3, correspond to all the points that are more than 3 units from 1 on the number line. Let's show that. Here is 1. 1, 2, 3 takes us to 4, and then anything that's farther away than 4 is greater than 3 units away from 1. Now to the left, 1, 2, 3, mark that spot, and then shade everything that's greater than 3 units away from 1. Therefore, the absolute value of x minus 1 is greater than 3 is equivalent to this combination of open sentences. X minus 1 is less than negative 3, or x minus 1 is greater than positive 3. We can solve this algebraically. Let's add 1. We get x is less than negative 2. Or, in this open sentence, let's also add 1. We get x is greater than 4. These combinations of open sentences are called compound sentences. When solving a compound sentence, you must decide if the solutions are to belong to at least one of the sentences or to both of the sentences. To help us decide that, let's look at two vocabulary words that have to do with sets of numbers. The first is the word union. The union of two sets, A and B, is the set consisting of elements belonging to at least one of the given sets. By the way, the symbol for union looks like this. This is A union B. As an example, let's say that A is the set 0, 1, and 2, and B is the set 2, 3, and 4. The union of A and B contains all of the elements that are in at least one of the sets, 0, 1, 2, 3, and 4. Another word is intersection. The intersection of two sets, A and B, is the set consisting of elements belonging to both given sets. The symbol for intersection looks like this. Using these same two sets from above, we can find the intersection of A and B. We're looking for elements that are in both sets. That's the number 2 only. Now that we have symbols for union and intersection, let's summarize the results from our 3 example problems about absolute value. An absolute value equation is equivalent to this compound sentence. X minus A equals negative B, union X minus A equals positive B. Ever see the word or written in the book? That means union. Our next example was an absolute value inequality that had a less than symbol in it. It is equivalent to this compound sentence. Negative B is less than X minus A, intersected with X minus A is less than B. It's more convenient to write the inequality like this. If you ever see the word and connecting inequalities together, that means intersection. Our third example was an absolute value inequality that had a greater than symbol. It's equivalent to X minus A is less than negative B, union X minus A is greater than B. Again, the word or means a union. Let's use these reminders to tackle the next example. On a number line, let's graph the solution set of this intersection. One sentence in the combination has absolute value, and there is a less than symbol. That fits this second situation. So let's follow the pattern up above. According to this second statement, the absolute values that have the is less than can be written using this combination setup. When it says negative B, we write negative 7. Then there's a less than symbol. When it says X minus A, we're going to write 2K plus 3. Then there's a less than symbol and the B. We're going to write less than the 7. Let's continue solving this. Subtract 3 from all members. Negative 10 is less than 2K is less than 4. Now divide by 2. Negative 5 is less than K is less than 2. That was only the first half of this combination. Now we have an intersection with the solution to this. So let's solve this one. Subtract 1 from both sides. We have negative K is greater than or equal to negative 1. Now divide by negative 1. We get K is less than or equal to 1. I divided by a negative, so I reverse the arrow. The next step is to think about what really is the solution for K. We're doing an intersection, so we can only have numbers for K that belong to both solution sets. It must be between negative 5 and 2, but at the same time, it must be less than or equal to 1. We need to combine those statements together. The final result is -5 is less than k is less than or equal to 1. Now we can graph that on the number line. -5 gets an open circle, +1 gets a closed dot, and we shade in between. Let's summarize the lesson. We discussed how to solve absolute value expressions by changing them into equivalent compound sentences. We also discussed unions and intersections. Unions correspond to the word or, and intersections correspond to the word and.